Hello students, I am Professor Sanjay Bhargav. In my two earlier videos, Electrostatics 1 and 2, we studied about certain basic properties of charge. We studied about charges at rest, then we studied about Coulomb's law, then we studied about superposition principle and concept of continuous charge distributions. Now, in this video, we are going to study electric field and its properties. We are going to study something about electric field lines and its properties. So, let us begin with electric field. The region of influence around a charge in which another charge on entering experiences a force. Suppose I have a charge here and this is its region of influence, in which suppose another charge enters and experiences a force, then this region of influence would be called as electric field. There are two types of charges. Source charge, what does it do? Produces electric field. Then there is a charge called test charge. What does it do? It detects and measures the electric field produced by the source charge. So a charge which produces an electric field is called a source charge. A charge which is used to detect and measure the electric field produced by the source charge is called a test charge. Remember, test charge is always positive, while the source charge can be positive or negative. If you remember, in superposition principle, in the second video, we calculated the force experienced by the test charge Q0 due to system of source charges Q1, Q2 and Qn. Now this force F is given by Q0 summation I is equal to 1 to n kqi upon ri square ri cap. This Q0 can be brought in the denominator, gives me F upon Q0 is equal to summation I is equal to 1 to n kqi upon ri ka square ri cap. Now look at the LHS of the equation. What does F represent? Force on the test charge. What does Q0 represent? Magnitude of the test charge. So what does LHS represent? We can say it's a pure function of test charge alone. While in the RHS, what does QI represent? Magnitude of the source charge. And what does RI represent? Its relative position. So RHS is a function of a magnitude of the source charges QIs and their relative positions RIs. Since LHS and RHS are mutually independent, so both can be equated to the same constant, and that constant is E, henceforth called as electric field. So what does E represent? Force per unit positive test charge, and is equal to summation kqi upon ri ka square ri cap. Here E would be known as electric field. Here E can be written as force upon Q0. We can write it with the limit Q0 tending to 0. That means the value of test charge must be as small as possible. Why? We'll see in the forthcoming discussion. What are the conclusions that I can draw? I can simply say electric field is numerically equal to the force that would be experienced by this test charge, that is a unit positive charge. So what I can say is, if Q0 is equal to 1 coulomb, then I can say force would be equal to the electric field. So electric field is numerically equal to the force experienced by a unit positive test charge placed at that point. The direction of the electric field is along the direction of force experienced by the test charge. Now here I have a charge, positive charge Q. Q0 is the test charge, that is also positive, so Q0 would be repelled by charge Q. So direction of the force is outward. So that would be the same as direction of electric field. Here I have a negative charge. I place a test charge here. Q0 would be attracted towards the negative charge. and that is why the direction of electric field is inwards. Both these figures represent the direction of electric field when the charge is positive and when the charge is negative. What is the unit of electric field? The unit of electric field is Newton per Coulomb. What are the dimensions? The dimensions are m1 L1 T power minus 2 for the force, ampere power 1 T power 1 for charge. So resulting dimensions are m1 L1 T power minus 3 ampere power minus 1. What is the electric field due to system of charges? It is equal to summation I is equal to 1 to n k qi upon ri ka square ri cap. We said test charge must be as small as possible. Why? So that it does not disturb the distribution of source charges and the change in electric field produced by the source charges. So test charge has to be small, because what is the role of the test charge? To detect and measure the exact value of the field produced by the source charge. If it disturbs the distribution of source charge, Ri would change and hence the electric field would change. So that is not desirable of a test charge, and that is why we say that test charge must be as small as possible. Now electric field due to isolated single charge. So we have a charge Q whose electric field is supposed to be measured at point P. For measuring electric field you require a test charge. So Q0 is placed at the point P, which is at a distance r from the origin. Now I can say a charge Q is placed at the origin. To measure the electric field at point P, we assume a test charge Q0 at point P. Force on the test charge Q0 upon r square. By definition, electric field is equal to F upon Q0, which would be equal to, that means you are bringing this Q0 on this side. So remaining part is KQ upon r square r cap. The direction of the electric field is along the direction of the force on the test charge. See in the figure. This positive charge would be repelling the test charge. So this is the direction of force and same is the direction of electric field. Now, the graphical way of description of electric field is through electric field lines. What is electric field line? It's a curve drawn in such a way that tangent at any point on the curve gives the direction of electric field at that point. Remember, I can draw a line of force like this. At this point, the direction of the tangent would give me the direction of electric field. Suppose I have a unit positive charge and place it in the electric field. It would move along certain path. The same path would be called as electric field line. So I can say an electric field line is the path along which a unit positive charge will move in space when placed in the electric field. Now, we have a positive charge and we have a negative charge. This represents the electric field lines for a positive charge and this represents electric field line for a negative charge. Now remember, if I place a charge Q0, that is test charge at this place, what will happen? It would be repelled in this direction. That is why we find all arrows outward. If I place a test charge at this point, then what happens? It would be attracted by the negative charge. So direction of field is inwards. Now what properties can we explain? We can say electric field is spherically symmetric. So what do we mean by it? Suppose a charge Q is placed at the center of the sphere. Then at every point on the surface of the sphere, the electric field would come out to be same in magnitude. That is what is called as spherically symmetric. Same in all directions on the surface of the sphere. The same property holds for the negative charge also. But when it comes to direction, we say electric field lines for a positive charge are radially outwards, that is away from the source charge, while electric field lines for a negative charge are radially inwards, that is towards the source charge. Now what are the important properties of the electric field lines? Electric field lines, they start from the positive charge and end at the negative charge. How do we say like this? Let us see here. These are starting from the positive charge and finally seem to end at the negative charge. Second property that we can think about is, for single charges, they may either start or end at infinity. So they start from here and end at infinity. They start from infinity and end at the charge. So both ways. For a positive charge, they are moving till up to infinity, and for negative charge, they move from infinity to the charge. The two field lines never intersect each other. Before that, I can say the direction of the tangent at any point on the field line gives the direction of electric field at that point, already discussed. Then we say two field lines never intersect. How do we come across? We say like this. We have a line here, we have an electric field line here. So on this field line, the tangent is in this direction. On this field line, the tangent is like this. So at the point of intersection, what are we observing? There are two directions of electric field, which is physically not possible. The next property is electric field lines are always perpendicular to the surface of the conductor. Suppose they are not, then what will happen? This is the electric field. It will have a perpendicular component, it will have a parallel component. Then I can say, what will the parallel component do? It would exert a force on free electrons which are present in the conductor. So here we are saying, if they are not, then what will happen? Component of electric field parallel to the surface of conductor would cause a force on free electrons, causing their acceleration, which is against the laws of electrostatics. Because in electrostatics, what we require? Charges at rest. So acceleration has to be zero. So force, charge on the electron is minus E. E parallel is the component, would be equal to mass times acceleration. So acceleration would be equal to minus E parallel upon M. If you want acceleration to be zero, E parallel needs to be zero. That means only one component would exist, and that is E perpendicular. And that is why we say electric field lines are always perpendicular to the surface of conductor. The number of field lines produced from a source charge is proportional to its magnitude. More is the magnitude of the charge, more would be the number of field lines. So we write here as number of field lines is directly proportional to magnitude of the source charge and proportional to Q. The relative density of the field lines at different points indicates the relative strength of electric field at those points. How do we think about? The number of field lines passing per unit area. This represents the area. This is the normal. So number of field lines passing per unit area would provide a measure of strength of the electric field at point. If the electric field lines are very close to each other, then field is strong. So we write crowded field lines represent a stronger field, while the spaced apart lines represent a weaker field. We have a word called neutral point. What does that mean? The point at which the net electric field is zero is called neutral point. At the neutral point, no field lines exist because the net field at this point is zero. Now we want to study electric field line pattern for a system of two positive charge. If we have two identical charges, they are supposed to repel. Repel means you can just see the field lines here are moving either this way and this way, showing repulsion. That means they are expanding. The lateral expansion explains the repulsion between two identical charges. What is lateral expansion? It means spreading of the field lines in perpendicular direction. So, field lines is spread when the two charges are identical. We also have to have an idea about electric field lines for an electric dipole. What is dipole? A system of two equal and opposite charges. So here we have a charge plus Q, here we have a charge minus Q. Now what is happening? Field lines start from the positive charge and end at the negative charge. They are very near to this axial axis. So we can say it as longitudinal contraction. Contraction along the length of the system. It explains attraction between two unlike charges. Longitudinal contraction means crowding of field lines along the length of the system. Now, we have a question here. In this question, you have to identify the polarity of Q and Q dash and find the ratio of Q dash upon Q. The charge Q dash is positive. Why? Because the field lines are moving outward and charge q is negative because the field lines are terminating at q. Now look, q dash, 6 field lines are moving outward, while from q only 3 field lines are terminating here. So the ratio of the magnitude q dash upon q would be n dash upon n, and is 6 upon 3, that is 2. So one can calculate the ratio of the charges, can also predict the polarity of the charges by looking at the field pattern. Hope the things are very clear to all of you. Thank you all. Let us meet once again in the next video. Once again, thank you.